Chapter 9b, A First Look at C++. This chapter is a whirlwind tour of the C++ language. We cover a lot of ground, but not in very much depth. This is just a quick introduction so you can get the feel of the language and what is available to you. The C++ language began with the work of Bjarne Stroustrup, who is from Denmark and who was employed and still is employed at Bell Labs. Of course, it's called AT&T Research Labs now. But he went there in about, 1979, I believe, and was working on some simulations. And he had been using a language called Simula 67 when he was in Scandinavia. That's a language that was developed in that part of the world. It's actually the world's first object-oriented programming language. 1967 is when it was developed. But he wasn't happy with the performance, and so he thought he would take a look at the C language and see what kind of features he could add. And so the first thing he did was add classes. Just this idea of being able to define your own types, which is a great boon to program organization. So he added objects to C, and the purpose, of course, was to get the best of both worlds, take the world's most efficient high-level programming language and add to it object orientation. Well, it caught on. It became public in 1985, and by the time 1990 came around, it was pretty clear that this language needed some standardization work because so many people were using it all over the world. And so the Standards Committee began working in March of 1991, and the standard was complete in July of 1998 and voted officially and accepted in November of 1998. So now we have an international standard for the C++ programming language. When C++ was being designed, compatibility with C was a very high priority. The only time the C subset of C++ acts differently is when it was necessary to change the rules a little bit to achieve the goals of C++. The goals of C++, the chief goals, were add object orientation, but also to be type safe, and if possible to improve upon the type safety that C has. There are certainly some holes in the rules of C that allow you to do some things to shoot yourself in the foot. And so here's a list of some of the changes that have been made to the C subset of C++. The first to mention is that a single character inside single quotes is a char, not an int, as it is in C. One of the reasons for that is so it can print out properly when you use streams, and we'll see that later. Also, as you know, a double-quoted string in C is an array of characters terminated by a null byte. But the type of that, as far as the compiler is concerned, in C is char star. The problem with that is that you can actually change one of those characters. For example, you can assign a literal to a pointer and then go through that pointer and make a change to any of those underlying characters if you had declared it as char star. You can't do that in C++ because they define a double-quoted string to be const char star. That certainly is the most common usage. You don't usually want to change a literal. Another difference is in the use of prototypes. In C, if you have a function definition, a function, a definition or a declaration, it doesn't really matter. If you define a function to take no arguments and you don't put anything in the parentheses when you define or declare the function, C will still allow you to pass it arguments, but it will not check them. Now, I didn't show you any examples of that, and you shouldn't be doing that either. And the only reason for that is, it's a historical reason because C always did that. But it's not good practice, and C++ does not allow it. And so if you define a function in C++ and you do not specify any parameters in the definition of that function, it's the same as if you had used the void keyword. In other words, no arguments are allowed. Another nice difference is that you can use const int declarations as dimensions for arrays once they've been defined. Once the integer has been defined, And that's nice because that way you don't have to use the #define mechanism, which is a preprocessor thing. So you can actually say const int n equals 100, say, and then you can declare an array and use n as the dimension. And then the final thing, which I know I have mentioned earlier, is that when you define a struct, the tag name automatically is a type name. That is, you don't have to use the keyword struct to declare a variable. You can just use the tag name itself. This program may look simple, but it really does illustrate a lot of differences between C and C++. What I'm trying to illustrate here is the usage of I/O streams, which is a different mechanism for input and output. You'll notice down in the main program, I have a thing called cout. Well, that's pretty much the same as standard out. It represents standard output. But it's a stream. It's what we call an I/O stream. In this case, it's, of course, an output stream. And what you can do with output streams, well, you use them for output, of course. There's a number of improvements in using those over using the normal output mechanism from C. Probably the first thing to mention is that when you output something with an output stream, you really can't make any of those mistakes like you could in printf, for example, getting the format wrong, and things could really get messed up. Because the stream takes a look at the type of the argument that is being inserted into the output stream. We call it inserted, meaning to give output to a stream. And since it knows what type it is, it just does the right thing. You don't have to worry about a format mismatch. So in this case, I'm saying cout, and then the left shift operator is overloaded, as we say. It has a multiple meaning. Not only is it used for shifting integers, but in this case, we have things that aren't integers. We have a stream on the left and a string on the right. And so the compiler can certainly differentiate that from integers. And the stream mechanism has the wherewithal to figure out how to output a string. And so it just does it correctly. The second thing being inserted there is a special term. End-L stands for end line. Let's back up a little bit. All this does, of course, is print out hello world. But if you'll take a look at the beginning of the program, you will notice that I am including a header called IO stream, but I do not say .h. Well, that's interesting. That's quite different than what you're used to in C, and even if you've been using C++ over the years, this is a change. Well, there's a reason for that. It turns out that the library, the C++ standard library, is not only partitioned into different headers, IO stream being one of them, but there's also a concept of namespace. Namespace is a packaging mechanism. It's a way to put names together as a single unit. And it turns out that a good 98% or 99% of the standard C++ library is in a single namespace called STD, which is an abbreviation for standard. The reason for this is so that you can take multiple libraries and use them in your program and not worry about name clashes, which can happen when you have multiple link libraries. The namespace is just another layer of wrapping that goes around a group of names. And there is a way, although I'm not going to take time to talk about it in these examples, there is a way to only use those names from that namespace package that you want. And so even if you have a couple of large libraries and you're using them at the same time, if they have names that are the same, you don't have a problem as long as you don't use the same names from each library. You only use a particular name from one and a different name from another, and there's no clash, and all the rest of the names remain hidden inside the namespace. Well, that's one of the reasons that namespaces are in the language. However, what I'm doing here actually is just unlocking the whole namespace. When I say using namespace std, that particular statement says, open up the namespace and look in there for any of the names that I happen to be using. And that's where it finds cout and end-L. Anyway, so this is just introducing the IOStreams mechanism The key feature about I/O streams is that it is a type-safe I/O facility because the stream just does the right thing according to the type of thing you insert into it. C++ also offers a new facility for doing dynamic memory. Instead of calling functions like malloc and free, where you give it a number of bytes that you want, in C++ you just say, give me a new object, give me a new thing. For example, give me a new int. Here I'm declaring IP as a pointer to int, and I'm initializing it with a new integer off the heap, and it's being initialized with the number 7. You can do that all at once. And so what will happen is some space will be allocated on the heap. It'll be initialized with the number 7, and the pointer to that space will be returned. When you're finished with a pointer to a heap object, you need to get rid of it. That is, you need to free the memory back to the heap. And whereas you did that with a call to the free function before, in C++ you use the delete operator. You just say delete and the name of the pointer. That's how things work for scalar objects. But if you want to allocate an array on the heap, there's a special syntax. First of all, you have to use the brackets when you're allocating it because you want to tell it how big you want it. So here I'm allocating an array of 10 ints on the heap and storing that in IAP. But there's a special syntax for deleting it. Whenever you delete an array on the heap, you have to say delete and then brackets. That together forms the array delete operator. It's extremely important that you get these things in the proper sequence. You should never use a regular delete without the brackets if you're deleting an array. So the rule is if you use brackets in the allocation, you should also use brackets when you call delete. Now, the other nice feature here is that these are compile time operators, meaning they're not function calls. The compiler, therefore, since it knows the size of the objects you're asking for, it will compute the number of bytes that you need, and you don't have to do it. You just say, give me a new one of these, and it figures it out. The other nice feature, although we don't have time to illustrate it, is that when you define your own structs, your own user-defined types, as it were, there is a way for you to specialize how those are initialized and how those are uninitialized. And those are special functions that go with your structs called a constructor and a destructor. And the nice thing is that when you call new, it automatically will call the constructor for your variable that you're declaring and initialize it as you want it to. It could be a complicated process. And furthermore, when you delete such an object off the heap, the destructor will automatically be called. So again, this idea of automatic initialization and cleanup, it not only happens in the new features of the language where you define your own types, but it's also automatic when you use things on the heap. One of the key features of C++ is that it supports objects. It's an object-oriented programming language. The notion of an object is not terribly unusual. It's based on the idea of a class. A class is really just a type. An object-oriented programming language allows you to define your own types. But even that is not a revolutionary concept. A new type in C++ is really nothing more than a struct that you also define functions with. So basically what you do is you define a struct like you normally would, but in addition to defining data members, you define member functions. And these functions can only be applied to an object of the type of the struct that you have defined. And there's a new keyword called class, and it's pretty much interchangeable with struct. There's only some minor differences between the two. But it's there just for emphasis because class is the term for that object-oriented concept of a user-defined type. When you define a class, either using the class or the struct keyword in C++, you not only can add member functions to the definition inside that class, but you can also specify whether they can be accessed by users or not. That is, you can have private sections where data and functions, according to your design, can only be accessed inside of one of the member functions of that class. In other words, a client who is using an object of this new type that you're defining cannot call those functions or cannot access that data because you have called it private. There's also a protected keyword too, which is a little less exclusionary than the private. Now again, as I mentioned on the previous slide, when you define your class, you can define special functions which will automatically be called when a new object is created to initialize it, and when an object is destroyed to clean up any resources that it might have used. And these are called constructors and destructors, respectively. Here I'm revisiting the stack example that we've seen previously. I'm going to rename it stack event instead of just stack, and you'll see why shortly. But here is a class defined in C++, which does pretty much the same thing as our stack did earlier. After the opening brace, and again remember class is pretty much the same as struct, I'm going to have two sections. One is a public section, and this is my interface. This declares those things that I'm going to give my users access to. So here you would expect to see all of the functions that a user needs to manage a stack. And here they are. Notice the first function has the same name as the class. And there is no create function like we had before. That's because this is a constructor. Whenever you have a member function with the same name as a class that it is inside, that makes it a constructor. What that means is that whenever you declare a variable of this type of object, that function will automatically be called. So in this case, the only constructor I have is one that requires an int. So that will be the only way that you can declare a variable of the stack event class, is by providing an int argument to initialize it with. That's of course what we want and what we had before with our create function. The rest of those functions are as we have seen before: push, pop, top, size, and they behave the same as they did before. But notice that none of these functions have a mention of a stack pointer or a stack of int star. The reason for that is because I'm defining these functions inside of the class. And as you'll see in the example shortly, I can only invoke these functions on behalf of a variable of this type. Therefore, there's no question on what struct instance these functions are operating on. So there's no need to explicitly pass it. It's all transparent. The final declaration in the public section is a destructor. And you can tell that because, like a constructor, it has the same name as the class, but it also has a tilde in front of it. So that is a destructor. Now these, of course, are just declarations, similar to what you would see in a header file. And as a matter of fact, you generally put class definitions in a header file. Now notice the private section. I've declared my data elements, which I had before, the pointer to int, which is the actual dynamic array. Length is how big it is, the maximum size, and pointer is the stack pointer, which is currently pointing to the next open slot, and which also represents how many elements are in the stack. This is the implementation file for the stack event class. So, as you're accustomed to doing already, I will include the header, which has the class definition. And here's where I will implement each of those functions. The difference that you'll see here is that each of those functions is declared to be a member of the stack event class, and you can tell that by the prefix stack event : The double colon is a scope resolution operator. It allows you to declare something to be part of another scope. So the scope we're talking about here is the class stack event. Now notice that inside of the stack event constructor implementation, that I can directly access data and length and pointer, the member variables. When we implemented these functions before, we had to use a pointer. We were being passed a pointer to a stack object and had to go through that pointer to get at those members. It's all automatic here because stack event is a member function of the stack event class, and there is always an existing object that is just there. And we'll see that in the test program in 2 slides from now. Well, there's the rest of the functions. Push, also declared as a member function of the stack event class, and likewise it has direct access to those private data members. Now these private data members cannot be accessed in a test program, in a client program, only inside of the member functions of the stack event class. Now I'm doing something a little different here to show an error condition. Again, I'm just trying to quickly give you a look at the things you can do in C++. Notice the keyword throw in the push function. That is the case where there was no more room to add an element to the stack, and so it overflowed. And the keyword throw throws an exception. It raises an exception. What that means is that that string overflow will be raised as an exception, and there better be what we call an exception handler in a test program. This is just a way of doing error handling without sending return codes. What's going to happen is that if for some reason this condition occurs, then an exception being thrown will cause the execution control to be transferred to some other point in your program that can handle that exception. I'm not going to illustrate that in this test program. I just wanted to show you that there is this mechanism for throwing exceptions. You can throw exceptions of any object type, and it alters the control flow of your program. And this is a very natural thing to do in a case like this. Whenever something goes wrong and there's really no way to fix it and you want to let your client know that something went wrong, you throw an exception. This is the implementation of the remaining member functions. Notice in the destructor at the bottom of the slide that I'm using the delete operator with brackets. If you recall, the constructor on the previous slide allocated the array on the heap to hold the integers of the stack. And since it's an array, I have to use the array form of the delete operator to free that memory back to the heap. Here's a test program that uses the stack event class. So I'll include intStack.h to get the class definition. And inside of my main program, I'll declare a stack event object. Notice I don't have to say struct stack event or class stack event. It's just a type name. C++ does that for you. I'll declare an object stack, stk, and I'm going to initialize it with the value n, which is 5 in this case. And so when the stack event object is constructed, that constructor function will receive 5 as the value, and so it will allocate space on the heap for 5 ints. Now here's where you can see the way that an object is used to call a member function. It uses the normal structure member syntax, which is the dot. What I'm doing in the for loop is I'm pushing the numbers 0 through 4 onto the stack. I say stack.push sub I. That push is the member function. It takes parameters like any other function can. In this case, a single int. That's the way we defined it. But notice that it is called in the context of an existing object using the member object syntax of a single period. So that push member function will be executed on behalf of the object stk. And that is all taken care of for you, and that's why we didn't have to worry about what the object was inside of our member function implementations. Well, once I push those onto the stack, now I will just empty the stack out, and of course we expect them to come in last in, first out order, which they do. So I can say while stack.size is greater than 0, in other words, while there are elements left on the stack, let's go ahead and call the pop member function and print that out at the same time. So we'll say cout gets stack.pop gets a space to keep them nicely separated. And when that loop is finished, I'll just do a new line and we're done. The stack event class is quite simple and sort of useful. But if you think about it for a moment, what if I wanted to do a stack of floats or a stack of employee objects? Is there anything really different about the logic of a stack and how it operates, whether I use an int or a float or any other type of contained object? It really makes no difference whatsoever. The logic of the operations of a stack is identical, totally independent of what you're holding in the stack. So for that reason, C++ supports what we call generic programming, that is type-independent programming. It allows us to define something like a stack, which is a typical container, and to define it in such a way that the type of object it contains is unspecified when we actually do the logic for the stack class. And then we can tell it when we want to use it what type we're going to contain, and then everything will just behave properly. And the facility that the language gives us to do that is called templates. A template is a way of defining a generic class or a generic function. And then when you actually get around to telling the compiler, oh, this is the type that I want you to use, by the way, well, that's called instantiating the template. And the compiler will generate the proper code. So it'll be just as if you typed it in yourself, like stack event where you specified int. But all you have to do is type the generic code once, and the compiler's job is to do all these special versions as you need them. To illustrate templates, we will rewrite the stack event class, as a generic stack template. So we won't call it stack event, we'll call it stack. And the way that we tell the compiler that this is a template, that this is a generic type class, is by preceding the class declaration with the word template, and then in angle brackets, the word class, and then a variable. I'm calling it T, which stands for type, and that's commonly used, but you can call it whatever you want. It is a type parameter. So this is a way of making the type be a parameter. Very different than a function which takes a value as a parameter. So what can change here is the type of the object we're containing. Now if you go inside of the definition of the stack template, it pretty much looks the same as stack event did, except wherever we had an int which represented the type of contained object, we replace it with our type parameter, which is T. So push takes a T instead, because we want to be able to push any type of object onto our stack. That is the type of object our stack is made to hold. Pop returns a T, top returns a T. Size, of course, still returns an int because that's an int. Size is a number, but all of those other instances are where it represents the type of object being contained. Also in our data, you can see that instead of int star data, we have T star data. Now the difference in the member functions you can see at the bottom of the slide, and it'll be this way for all of the member function definitions. It will be just like we had it before, except we precede our function definition with template class T. That tells the compiler that this is a function template. And then, as usual, we have to have the name of the class followed by a double colon, and then everything else is as you would expect. But notice what the name of the class is. It's stack of T. That is, the T is in angle brackets. It's not stack, because stack is a template. It's a generic mechanism from which classes can be instantiated. It's only when you decide what T is that the compiler is going to generate a specific class. So stack of T represents the concept of what the class is, and so that's why that is what precedes the double colon. Here's the implementation of some of the other functions, and again you see the same pattern established in the previous slide, where we begin the member function definition with template class T, and then where we had stack event before, we put stack of T before the double colon, and then there's a T everywhere where there used to be an int when it's in the context of the type of contained object. Other than that, Nothing else has changed. In the test program here, you'll see one sequence from the way we used it before, and that is in the second line of main. Here I'm actually telling it what type of stack I want. In other words, what is the type of the contained object that I'm putting on the stack? And to be different, instead of doing ints here, I'm doing float. But of course, you can do any type you want to. That's the neat thing about templates. So I say stack of float, stack, STK, of n. So that works like I had before. It'll initialize the stack with 5 spaces on it. But it will allow me to only put floats on there. In other words, the compiler will generate source code as if I had defined a class named, something, stack of float. The actual name of the class is not important. And it will generate all of those member functions with float in place of t. And so that's what makes this a stack that can hold floats. So I'll just go through and put some numbers on there. Notice that I'm pushing I plus 0.05, and so we'll get 0.5, 1.5, 2.5, etc. being pushed onto the stack. And so it's able to handle floats, and then I print them out and they come out in the right order. So the key thing is that you have to specify the type parameter when you instantiate the template. Well, that's all we're going to look at right now. There's certainly a lot more to say about C++. But what I wanted to show you is that, first of all, type safety is important in C++, and that's why IO streams behave the way they do. That's why we have private keyword. There's a lot of things in the language that make it safer than the C programming language. One related topic there as far as type safety is new and delete. It's a lot easier to use the heap with new and delete than it is to use malloc and free like you do in C. To support objects, C++ allows you to add member functions to your structs, and we use the class keyword usually, although you still could use the struct keyword if you wanted to, but it's considered better style to use class whenever you define a struct that has member functions. And then finally, an extremely powerful feature of C++ is templates. It allows you to write a generic template or pattern for code generation, and then the compiler will instantiate it for you whenever you ask for it. In this exercise, all I want you to do is take the employee struct and its associated member functions, as you have already used in the previous section, and to make it a class, a C++ class. So, for example, just use the keyword private for the data and put the interface functions in the public section. For the purposes of this, you'll have to put the class definition back into the header file. Remember, we had removed it when we used the incomplete type. You might even want to just start with the version from Chapter 7 if you find that easier. All I really want you to do is to define an employee class that has the data private and has the member functions that you need so that you can do the same sample program that we had before. In fact, I have it on the next slide for you all ready to go. All you have to do is do the class definition in employee.h and the implementation of the member functions in employee.cpp and compile and link them together. Here's the test program. It's pretty self-explanatory. Just notice that the key difference here is that I'm using the dot operator to call the member functions on the existing objects. Other than that, it looks pretty much the same as the test program that we had before. Well, that's it, folks. Thanks a lot. It's been good to go through this with you. And you're definitely ready now to move on.